Hello everyone, and today in this video I will talk about the Boolean fracture. In the last video I talked about the Voronoi-fracture, and Boolean fracture is just a fracturing method. So in this video I will also use the Voronoi-fracture so we can revise it, but my main focus will be on the Boolean fracture because it is really cool and a really important step to create the fracture pieces, and we will create this tearing effect step by step, and you will understand the Boolean fracture in depth. And we will also use the scatter method. We'll scatter the points and we will like R direct where the points will be high intensity and where it will be low intensity, so we can have the high density of these pieces, and in this part we have the low density of these fractured pieces. So let's start without any wasting our time further. So you will see for this I have this exploded view, and you'll see we have all the pieces separate. So let's start. We will create this network together, and to like explain first, we have this hand geometry, and uh, I will provide this hand geometry in the description so you can like do the same drill as I will do. So let's start. To like use this hand geometry in the same project, we don't need to use the wire. We have this object merge node, and this object merge node will give us this hand geometry. We just need to give this a location of our hand. So for this I have something like out hand, and now we have this hand geometry here. You see this out hand is the last node of this network, and this is just an alembic file of this. I will give you this file in the description, so no need to worry about this. So I have something like this. Now let's do the main stuff. Okay. First, what we need two things: our geometry to fracture, and like the Voronoi fracture, when we used the points, and then created those pieces by using those points, we will need those points, and we will create the Voronoi fracture again. And just ignore these white stuff on my face. This is just benzoyl peroxide. It is for my pimple, so I just ignore it. So okay, we have this hand. Now let's create something. So first, just scatter some points onto this hand. We will see something like this, and in the scatter node just turn off force total count, and I can turn off the max point limit and relax iterations, and by the density you can say I want 15 or 10 maybe is enough for now, because I will be like I will be using my own points, so no need to worry about density for now. So I have the scatter node. We need now a bound. So what I'm doing, I will explain it later, and you will understand this like really good. So what we can do is I will use the bound. Now what I'm doing here, I will use these points to create fracture in this bound by the Voronoi method as we did in the last video. So just say Voronoi fracture, and we have this bound and we have these points, and we will create those fractures. So now we have these fractures, and you remember Voronoi fracture gives us two groups, an inside group and an outside group. Inside group we have the interior parts, and I can show you by this blast node. I can say outside, and you see these are the inside part we have for now. So these scatter points created these cuts, and in the last video I explained about this in detail, so I won't be wasting time on this because we have Boolean fracture to study about. So we have this inside group. What I want here, I want the inside group for the fracture planes that we will use in the Boolean method. And let's explain what Boolean method is. So Boolean method is another way of breaking geometry into pieces, but we need two things. Like Voronoi fracture, we needed the points to create the Voronoi cells, but here Boolean fracture needs cutting planes or cutting geometry. It's like you have a box, and if you have a plane as a cutting geometry that is going through the box, then we will create two things, and it will act as a razor blade to cut the geometry. Sorry for that. And what I can do right now, I need the inner geometry for those cutting planes. So what I can do right now, I can just say blast, and for this blast I only want the inside. I only want this inside. Now we have two issues with this. We have overlapping faces, and if I just say primitives and select this face, and if I move this outside, you will see we have two overlapping faces here, right? Just delete this edit, we don't need. And we also have some overlapping points. You will see here we have like these points, but you see like this point is the common point for this part, and this part. So we don't have only one point. And how you can see this, just open the geometry spreadsheet and you will see how many total points we have. We have 15,415 points in total. But if I fuse this, fuse here mean we are fusing points that are overlapping on each other. So when I toggle this on, you will see our points count decrease drastically, right? Now we have 4,200 points instead of 15,400 points. So now you know the difference, right? So now the overlapping points are gone. Now we only have one point sharing these different holes, right? And you see this overlapping faces, you see this jittering, that means we have some overlapping faces. How we can like correct this? What you can use is here, remove overlap face. And I want to tell you something, that this node is from side effects labs, so you need to install side effects labs in order to use this node. It's really easy. You can just search on YouTube how to install side effects labs, and there are plenty of videos you can use. And if you are even using Houdini Apprentice, you can use the side effects like I'm doing. So just remove overlap pairs, and now we have sorry what you need to do instead, like we have two things. We have remove overlap pair and we have remove overlap. So we have to use the remove overlap, this one. So when you toggle this on, you will see something like this. This is a new node for me, so that's why. So now we have something like this. This will act as our cutting geometry, and how I will tell you in a bit. So we have this. Let's just template our hand. You see this hand. So now what we can do here, we can have some details in this, right? Okay, I will show you in a bit, but first let's now do the main thing, Boolean fracture. So this is for the geometry to fracture, and this is the cutting surface. This will be our cutting surface and this will be our geometry. If I want to say like how I can explain this object merge better, I said this is just the transportation, like what's the word, teleportation of the geometry, like in a single object, in a single project, or in different containers. How you can use this, like you can just create another object merge, or you can duplicate this. I'm creating this again to show you, and you can just give this the same path, and you will have your geometry right here. So you can use your geometry like many times without copying it, or without like making the connection all over the this project. You can use just object merge again and use this geometry again. So this is just a really cool node. Now we have this Boolean fracture. Now we have our geometry to create the pieces, and we have our like these cutting planes. So we will see something like this, and you will see we are seeing something like this. Okay, now it is giving us an error, and what this error says, let's see. So when we click on the I button, you will see we have one warning: crossed boundary unshared edges. That means our geometry is open. It is not a closed geometry. And we have in the Boolean fracture, we have this option treat geometry as. We have two options, a solid and a surface. For this is an open geometry, so we use surface. And when you use surface, you will see now we have our fractured hand. And just say exploded view, and you will see something like this. Our setup works, right? And here you will see these cuts are really sharp, right? And in the example I showed, you see these cuts are not this sharp, they have much more detail, right? So here what I can do this, we can give details to the cutting edges, and we can have the same details in our hand. So after this, these are our cutting edges, and what I can do here, I can give this a remesh. First, before giving this a mountain will give this a noise will give this detail. Before using the mountain to give this detail, we will use this remesh to give this much detail, so the mountain node can work on this, right? For this, I will say 0.1, and it depends on your hardware, like how much time it will take and how low you can go with this target size. But I will say don't go as low, like below 0.1, because it takes like it can be really heavy if you just decrease your target size below 0.01. For this I'm going with 0.07, and you see this. Now we have much more detail, right? Before before connecting this to the Boolean fracture, I want to give this more detail, and I'm going to use mountain node for this, and you will see now we have much more detail. Just turn this off, noise along vector, and decrease this amplitude, and let's say 0.22, I guess is enough. And you can increase or decrease the element size, something like this. And I want to say You can give this Berlin, but simplex works fine, and give this another mountain node to create another layer of noise on top of this. And for this I will use more noise. Let's say my main thing here is to like have really low element size. We have something like this, and let's increase the amplitude a bit. So now you will see we will have something like this. Now we have much more detail in our pieces, but the main thing happens now. You have all the details you have, right? We have this cool network, but really important thing here is you see these pieces have a constant, a similar density. Like you will see this has same number of pieces as this. I'm talking about the density of pieces. And why this is happening? Because we have these scatter points, like they have the similar density all over this end. But what if I want to have more pieces here and want to have less pieces here? How we can do that? What we need to do here is we need to give this part of the hand more density of points, right? How we can do this? You see this scatter node have this cool feature, this density attribute. So what this is saying, that we have this density, so whatever the density is high, we will have more points. And not only density, we have another attributes. We can create our own attribute and just place this on over the points of the hands, and we can scatter points according to that. So what we can do, I can just create attribute VOP, and we can create our own attribute. Inside this what we need to use the ramp. Why? Because this hand, wait a second, I will just template this. And okay, we have this hand, right? And this hand goes from this part to this part. If I like turn on our like template, our bounding box, you will see we have something like this. Now if we want to give like more density here and less density here, we need something, and ramp work best here, because we cannot like just manually give each point a number of that attribute, right? So to use the ramp, we need to feed the ramp numbers from 0 to 1, right? This is the first rule of using the ramp. So let's say you have this ramp parameter, and this ramp parameter needs to have values from 0 to 1 according to the points we have. So to give this, we will use relative to bounding box, and this relative to bounding box will create parametric coordinates. And this parametric coordinates is really important. I talked about this when I was talking about, I guess, early in this series, when I talked about the VOPs, right? I used about this relative to bounding box, and I will explain this again. This is the values relative to the bounding box this hand has, not this bounding box. This is not. This is an internal bounding box. We are using this bounding box, right, for a reference, and we are giving the numbers from this side to this side from 0 to 1. So these points will get value according to their position according to this bounding box, that they will have the values, and those values we call that parametric coordinates. Parametric coordinates are the local coordinates that exist on the geometry. So it says where this point exists on this geometry according to this location, according to the whole geometry, not according to this world. So we have this relative to bounding box, and we are referencing the point positions. So this bounding box have the data. It has vector, position is in vector. Fuck these dogs. So now when we have the parametric coordinatic value, now what we need to feed this value into the ramp. But when I connect this into the CD, you will see now these points have some colors. Why? Because color is also a vector. We have R, G and B. That means we are getting 3 values from this, because position is a vector also. So but I don't need 3 things. So we are getting 3 values right now, and we are feeding it into the CD attribute. But we don't need 3 value, we need only 1 value. For this, I will use the vector to float. Now we are getting something like this. When I connect the Y, when I connect the Z, if I connect the X, we are getting something like this. This part is getting 0, this part is getting 1. And how I can tell that? I can tell this by this part is black, this part is white. White means value 1, black means value 0. So let's feed this into the ramp. Now this ramp is RGB. I want this spline float value. You will see this ramp, we are feeding it into the CD attribute, but we can create our own attribute, or we can use the density. Bind export. I will say this density, or we can say our scatter density, right? Because it's our attribute, we can name this anything. So we have this ramp value, right? And I want to also fit range this value, because what if I don't want to use the value 0, I want to use the value 1. So fit range, I also talked about this in detail, and fit range means that if the value is coming from 0 to 1, and we have the spectrum of values from 0 to 1, and we want to like use this value into another range, let's say for range from 1 to 2, then how we will convert this? We will convert that value by this fit range. We know that the source minimum, the value that is coming out from this ramp is 0, from 0 to 1, and the destination now we want is from 0, 1 to 2. 2. So now we have something like this, and I want to see what is happening. So I will just connect this into the CD value so we can visualize this. We have this ramp, and I want to promote these two right here, so we can use this right. Okay, so we have something like this, right? And 0 to 1, let's say 0 and 1. So we are not doing anything by the fit range, we are just seeing what we are getting. So we are getting this value, and when you open the geometry spreadsheet, you will have this scatter density, and it will go from 0 to 1. We will have some points with value 0. We definitely have. So right now we have something like this. And scatter, I want to use our own attribute, that is scatter density. Now you see here that the scatter density attribute that is coming from here, we are seeing something like this. This black area will have less points and this part will have more points, but uh, I want the reverse. I want this part to have more points and this part to have less points, so we will just reverse this. And you see now this fit range value will come in handy, because now the minimum value we are getting is 0, but we don't want 0. I want something 0.5 on this part, and this area I want more, 3.5, or let's say 3.7. So you see this part, and what I can do, I can just make this B-spline, because we want to have the smooth curve instead of that harsh curve. We can use the B-spline, and I can say I want more points on this part and less points on this part. So we will have something like this, right? So this is what I want to tell you. You see, now we have points, and we will create this Voronoi grid, then we use fuse this, then we will remove the overlap, then we will remesh this. Wait a second. Okay, and then we will use the mountain to give this noise, then we will use another mountain on top of that, then we'll create the Boolean fracture, and then in the end we will have our geometry ready to go. And you see this part is really big, and we have this tiny little part here. We can change this if we go in, let's say here, and I want to have like much more points here. I can use this, and probably this will break into pieces. Nope, it didn't. And we can use like more points if you want to break this. Let's say 1, then probably it will break. Still, where is this remove fuse? What we have here is mountain. It should like break into piece. Template this. Okay, I know why. Let's give this part 0.5 and you see why this piece is not like breaking, because our cutters is not going through. It is not going through this piece. So what we can do right now, we can just go in our, let's say, Voronoi, and we can, I want to show you really cool thing here, and that is to make this thing more efficient. And how we can do that, we can create after this mountain, we can create a group, and this group will be from this object, and I want to say fill polyfill. And what this polyfill will do, and I will explain how we can split this part. This polyfill will fill this geometry from this part, because if we want to say VDB from polygons, we need to have a closed geometry. This will use as this, and I want to have the bounding region and by volumes, and you will see something like this. So what is happening right now, I'm creating a group by the points by this bounding region, and I have talked about this in the groups video I created earlier. So now we have all these points in this group, and what I can use, I can say blast, and this group I want to say OS, and I want to give this cutting. Now you see what I did. I just created a group of these points that exist inside this hand of this geometry, and I blasted the outer part, and now we have more efficient here, more efficient. And why this is not cutting? Because our cutting edge is not going uh, outwards of this geometry, going through this geometry. And what I need to do here, I need to like rotate this object here to do so, and it will not break anything. You see this bounding box, this hand exists here. If I want to have this, I can just increase the bounds, lower padding. Let's okay, wait, cancel this and just see this, and this geometry just delete this, create another bounding box, bounds, and toggle this on. Fuck these dogs. And what I want to say, a wireframe, and template this. So I will just increase the padding and this padding also, and you will see now we will have more efficient way of cutting this geometry. It can take time for the first time when it calculates. So yes, and now when I just when I say this, you will see now we have our pieces separate. So you will see this piece, we can increase the ISO surface, so we can have more wait, you will see something. Okay, when I say this and this, say this or this, you will see something like, you see these points now, this is perfect, and we have, see, now our cutting planes are getting through this surface of the geometry, and we have something like this. So I guess, I hope you learned something from this video, and we have this cool trick, and if you want you can just decrease the number of points at this position of the hand, so you can have like more bigger pieces. Just let it remesh, and we'll have something like this. I guess this is it for this video, and when we connect this you will see nothing, and now we have something like this. So this is it for this video, and I hope you understand what Boolean fracture is and how we can scatter points at some places, how we can increase the density of the points at some places. And I guess this is it. So we have covered Voronoi, and we have also covered today Boolean, and in the next video maybe I will cover the different fracturing method or another drill, or maybe I will continue with the course. So let's see, and I will see you in the next video. Until then, take care.